Hi there. Welcome back to our course on advanced quantum mechanics. This is lecture 29. Remember, we arrived at the following question. How do we describe composite quantum systems? Composite quantum systems. The way we arrived at this question is that we said, consider some quantum system and then imagine that there is some measurement apparatus. And we said, okay, normally we consider the quantum system as the object of investigation, and then there's the rest of the universe around it, part of which is the measurement apparatus. But then we said, it should be interesting to do a Heisenberg cut around both and consider the quantum system in question and the measurement apparatus together to be one quantum system, and then do the quantum analysis of that, of its dynamics. In practice, this could be, for example, that we have an atom. That would be the quantum system of interest. And then the measurement apparatus, if we can call it that we use to measure the atom is just some lonely electron that comes along and scatters off our atom. This electron will then pick up some information about the atom, where it is or how fast it is and so on. So we have really two quantum systems, the atom and the electron. And the electron is, of course, the smallest measurement apparatus one can imagine. Of course, a single photon could also serve that purpose. Well, and then again, we could ask, well, what if we combine the two of them into one big quantum system? Then how do we describe that? Or another circumstance is that we have, let's say, an atom and another atom and another atom. Each one of them we could describe as a quantum system, but we might be interested in the molecule that they form. So then what's the quantum mechanics of the molecule? Or, and that's also a very important circumstance, imagine we're dealing with an atom, such as the hydrogen atom. If we do the quantum mechanics of the hydrogen atom, remember it has energy eigenstates, the energy levels of the hydrogen atom. I'm sure you've seen that in the previous course in some detail. Well, being energy eigenstates, these states are stable, right? An energy eigenstate doesn't evolve. There's no dynamics. In fact, nothing changes in the quantum system if it's in an energy eigenstate. Remember the time, energy, and cylinder principle. But that doesn't describe nature very well. When a hydrogen atom is in its fifth excited state, well, how long is it going to stay there? Not very long. It's going to decay into lower energetic states, eventually arriving at the ground state of the hydrogen atom, while emitting the difference in energy in the form of photons. We cannot calculate that if we only consider the hydrogen atom in isolation. No, we need to consider another quantum system as well, and that's the electromagnetic field. This too is a quantum system. It consists of infinitely many harmonic oscillators, one harmonic oscillator for every wavelength, in fact, for every wave vector. But that can be done. You can quantize those harmonic oscillators, and you get the quantum theory of the electromagnetic field. And then if you do a Heisenberg cut around both of them, and you see this is now more of a conceptual cut, not a spatial cut. If you do that Heisenberg cut around the atom and the electromagnetic field, then in that combined system, you can describe emission and absorption processes. For example, if you want to describe a laser, that's the quantum system you would need to consider. So in order to develop the quantum mechanical machinery to handle all of those situations here, we can approach that problem in two directions. One direction is that we start with the quantum theory of the bigger system, and then we learn how to break it down into two subsystems. That's a perfectly legal way to do it. But we can also do it from the bottom up. We can start with an atom and an electron, each having their own Hamiltonian, each having their own Hilbert space, each having their own observables. And then we combine these two quantum systems into one bigger quantum system. The same for all the other scenarios here. We can study the quantum theories of the individual systems individually and then combine them into a bigger system. We have to choose one approach, and let's choose this approach, the bottom-up approach, where we start with the quantum mechanics of one system, the quantum mechanics of another system, and then we combine them into the quantum mechanics of the combined system. In principle, there's nothing new, right? Because we can already, with the formalism that we developed in this course, describe systems that are arbitrarily large. We just have to learn how to break them down into pieces. And similarly, now that we have, let's say if we have pieces, we can learn how to glue them together to get a bigger quantum system. So that's what we will do here now. So imagine, generally, we simply have two systems. We have a system that we may call A, and we may have another quantum system that we may call B. And we are interested in constructing the quantum system AB, which consists of both of them. Now, what that means is we will have to figure out how to construct, given system A, that is to say, given its Hilbert space, its operators, its observables, its Hamiltonian, and given for system B, its Hilbert space, its observables, its Hamiltonian. Given these, we should be able to construct what the Hilbert space and the observables of the bigger system are. Okay, so how do we do this mathematically? First, we will study what the Hilbert space is of the big unified system. And then we will study what the set of operators is that acts on this, on the Hilbert space of the big system. So this is non-trivial because the observables in A, for example, are operators that act on the Hilbert space of A. And the observables of B are acting on the Hilbert space of B. None of them acts on the Hilbert space of AB. But clearly, an observable of system A must be an observable also of system AB. It is literally observable, no matter how we choose our Heisenberg cut. So we will have to find out how we identify operators that are originally from system A as operators that can act, how an observable of system A can be represented either as an operator on the Hilbert space of A, or also as an operator, a different operator, that acts on the combined Hilbert space of the combined system. All right. In the process, we will find out today what is entanglement. So, first question is, what is the Hilbert space HAB? We assume that we know what the Hilbert space is of system A and the Hilbert space of system B. What is the Hilbert space of the combined system? We start with this definition. For every vector psi in the Hilbert space of system A and phi that is an element of the Hilbert space of system B, we define a vector which we will denote by psi tensor phi. At the moment, by writing this, we are really just inventing a way of writing things. Okay, so I'm not assuming that you know anything about this symbol. Everything that we will do with these definitions now will arise. I'm not assuming that you know anything about this symbol, which will be called tensor product, just yet. Okay, so just take it as literally of what this says. You take one vector from one Hilbert space, you take another vector from another Hilbert, from the other Hilbert space, and then you can pair them up, and you use this funny symbol here in the middle to denote that you pair them up. And then we declare that this is a vector in the Hilbert space of HAB. But not only those. The definition is that the set of all psi tensor phi together with all of their finite linear combinations is called this is what we will call HAB, which is called HA tensor HB. Right? So we're just giving names to these things. Elements, element of HA tensor HB, and that's the thing that we will call HAB, are of the form sum over I, or sum over n, let's say sum over n. No, I don't want you to think that these are basis vectors. They don't have to be. So it's psi I tensor phi I. Right? So these guys are elements of H A tensor H B. All right, so far, this is simply saying that if we have a state or a vector of one system and a state correspondingly a vector of the other system, then the total system could be described by having the one vector and the other vector, right? So we have to invent some symbol to say that we consider both of them, and that symbol is this tensor product symbol here. Let's spell this out. Tensor product symbol. So far, that's just the bookkeeping. We are saying that, sure, if the A system A is in the state psi and system B is in the state phi, then the total system can be described by just keeping track of both of them. That's what we have in here. This is just a bookkeeping that, okay, the first system is in that state, the second system is in this state. Okay, so far so good. But we remember, of course, that for a quantum system, if it is the case that if it can be in one state, or in another state, then it can also be in any linear combination of these two states. And that's the reason why the definition of the space HA tensor HB is such that it contains not just the pairings, but also the linear combinations of those pairings. Right? It's clear that every psi tensor phi must be part of the Hilbert space of the big system, right? Because if we know this subsystem is in this state and that subsystem is in that state, then clearly the state of the full system has to be, yeah, well, those two states collected together, and the tensor product symbol is indicating collected together. But our system could be in state psi tensor phi plus some number times psi tilde tensor phi tilde too. For any quantum system, in any context, whatever states it might be in, it can also be in the linear combination of them, right? Because we know from our earlier considerations in this course that the states form a vector space. That's why we had to include here not just these basic tensor products, but also their linear combinations. And what this is telling us is already that, maybe the quantum theory of the combination of the composition of two subsystems is richer than just the theory of one subsystem and the theory of another subsystem. And that's because as long as these two subsystems are completely uncorrelated, completely independent, all we need to know is what is the state of one system and what is the state of the other system, and we can smash them together with a tensor product and we know everything about the total system. But what we see here is that because of the linearity of quantum mechanics, because any linear combination of states can arise, we also have these linear combinations of these elementary tensor products. And that's something that cannot be described as being just part of the subsystems. For this reason, a definition, in order to capture this richness of quantum mechanics, this richness of the composition of systems as being more than just the sum of its parts, this motivates the following definition. All states, or all vectors, we should say all vectors in HA tensor HB, which are of the form psi tensor phi, are called unentangled. This is what you get if two systems have nothing to do with each other and you draw a Heisenberg cut around them. Unentangled states, right? Just one state for one system, one state for the other system. All right. Then the definition is that all vectors in HA tensor HB that cannot be written in this form are called entangled. Now, we notice, I will come back to the business of entanglement, of course, every now and then in this course and also later in this lecture. Now we notice that the Hilbert space, the vector space, no, let's just say the set HAB, which is by definition HA tensor HB, is inheriting a complex vector space structure, complex vector space structure from its constituents, namely from HA and HB. Remember that HA and HB are Hilbert spaces, which means that they are complex vector spaces. And of course, they have more structure too, which is that they have an inner product and that they are complete, that they have a notion of norm and a notion of distance, and then a notion of limit taking, and then from that you get a notion of completeness. But the very first notion that we defined for Hilbert spaces is that they are complex vector spaces. And now I'm saying that our vectors, our set HAB, which consists of all the linear combination, all the formal linear combinations of these guys, inherits from the complex vector space structure of HA and the complex vector space structure of HB, itself a complex vector space structure. Of course, ultimately, we want to see that HAB has its own Hilbert space structure, full Hilbert space structure. We know that this must be possible because everything in quantum mechanics, everything in the universe is quantum mechanics, is quantum mechanical, and therefore, whatever Heisenberg card we choose, we get a quantum system with its own Hilbert space. So our aim here is to build up that Hilbert space of the system AB from the Hilbert space structure of HA and HB. So how is it that that HAB is inheriting complex vector space structure from its constituent Hilbert spaces? Well, the answer is that for all, let me do it this way. Okay, for all alpha, alpha 1, and alpha 2 complex numbers, we have, and these are the inheritance rules. Inheritance rules. We have that alpha and then psi tensor phi. This is the same. So what you get here is that you have a vector and you multiply it with a number. That's the same as if you took the vector, multiplied it with the first vector, and then take the tensor product with phi. And this is, again, the same as if you took psi, and then you take alpha phi. This is how the linearity is inherited, how this part of the linearity is inherited from the Hilbert space structure of the constituent systems. But also we have that alpha 1, psi 1 plus alpha 2, psi 2, psi 2. If we linearly combine some vectors in the first Hilbert space, and then tensor that with a vector phi, then this is alpha 1, psi 1, tensor phi plus alpha 2, psi 2, tensor phi. And finally, we can play this game also with the right-hand side. So there we have alpha 1, some vector phi 1 plus alpha 2, some vector phi 2. This then is alpha 1 psi tensor phi 1 plus alpha 2 psi tensor phi 2, and can show that this makes HA tensor HB a complex vector space. Now, from this linearity, we should derive, on one hand, comfort, because it means we now know how to operate with the vector spaces here. These rules are all you need in order to handle any kind of calculation that you have that involves the tensor product of vectors. Because this tells you what you can and what you cannot do. It tells you how to distribute, right? This is a distributive law here, where you have psi tensor and then the sum of things, you get the tensor plus the tensor. So on one hand, this is reassuring. We now know what the rules are of the game when you have two Hilbert spaces and you form the tensor product Hilbert space between the two. In fact, so far, it's just a complex vector space. We will get to the Hilbert space structure in a moment. But if you look at it very carefully, you will see that due to the extra richness of the combined system that comes about because of the linear combinations, this notion of entanglement that we defined before, actually has some unexpected non-triviality. So note of caution. So remember, a vector is called unentangled if and only if it is of the form psi tensor phi, where psi is some vector in the Hilbert space of the first system and phi is some vector in the Hilbert space of the second system. That's when a vector is called unentangled. Otherwise, it is called entangled. Now, why is this non-trivial? Well, sometimes it is not obvious, but the case. You can have states that are unentangled, but they look like they're entangled. For example, let's say we define the vector omega, an element of HAB. If you remember, this is HA tensor HB. And we define this state omega to be psi tensor phi plus psi tensor var phi. This state looks unentangled, right? This state looks entangled because it's the linear combination of two such vectors here. But actually, it is an unentangled state. And why is that? Well, it's because if you look at the rules that we had up here, and in the last rule here, you see that psi tensor phi 1 plus psi tensor phi 2 is psi tensor phi 1 plus phi 2. So that means that because of the linearity in this business, this is equal to psi tensor phi plus var phi. Now this thing can be given another name. So let's say we call this vector here mu. This is a vector in HB, right? And that is a vector in HA. So therefore, what we have here is that this is psi tensor mu. And therefore, the state omega is unentangled. Even though initially it might have looked as if it was entangled. So it's unentangled. This is a very simple scenario, but there could be more complicated scenarios where it, again, is not obvious that the terms can be, there might be lots of terms, and then maybe somehow they can be rearranged, and bang, you're just left with a tensor product of two vectors, and it's unentangled. Okay, so we'll have to be careful about this, and we will eventually get a criterion for checking systematically whether or not a vector in HAB is entangled or not. In fact, we will also measure how much it is entangled. For example, I mean, just a simple example, if we have a state omega, which is, let's say, psi tensor phi plus 10 to the power minus 100, and then here we have some alpha tensor beta. Now, if alpha is not equal to psi and beta is not equal to phi, then this is an entangled state. But you see, it's just barely entangled because the prefactor here is tiny. So we can almost forget about this second term. It's not going to matter in experiments. It's so tiny. So the state is almost unentangled, but it is entangled. And so it is worth quantifying how much a state is entangled. And we will get to this later, not today, but we will get to this later on. Now the Hilbert space of the combined system AB is more than just a complex vector space. It's an entire Hilbert space. So in particular, there's a dual to it, a dual Hilbert space to it, and it has an inner product. And there's a norm, there's a length of vectors, and then there's a distance of vectors and topology and so on. So all of this structure is inherited from the Hilbert space structure of the constituent systems. So in particular, the elements of the dual space HAB dual are, well, there are two kinds. There are the simple elements, the unentangled elements, entangled elements of HAB dual are of the form, or can be brought into the form, psi tensor phi for all psi and phi, well, psi for all psi in HA dual and all phi in HB dual. This is meant to be a star here. And then the entangled elements are of the form, and the entangled elements of HA B star are of the form, and I think you're anticipating it, they are of the form linear combinations of vectors of this type. And for now, we keep it at finite linear combinations, that is to say, just finitely many terms, because we haven't quite clarified yet what the length, how the length of such a vector is to be calculated. And then eventually, of course, we'll keep that length finite. And then once we know what the length is, what the norm of a vector is in this in the Hilbert space of the combined system and its dual, then we can sum over infinitely many terms as long as the length of the resulting vector is finite. Okay, so then we have a Hermitian conjugation map. All of this is very much in parallel to what we did earlier in the course when we first derived the Hilbert space structure of quantum mechanics. So we have a Hermitian conjugation map. Dagger. And how does it operate? Well, when we apply it to psi tensor phi, which is a vector in our Hilbert space HAB. So if we do the Hermitian conjugation on that, we get this vector, psi tensor phi, which is an element, I should write an element of HAB star. Now, once we have the Hermitian conjugation map, this induces an inner product. So obtain, it's all completely in parallel to what we did earlier in the course, obtain inner product or scalar product in HAB. Let me remind you, it's also written as HA tensor HB. And how does that inner product work? Well, let's say we take two vectors. We take psi2 tensor phi2. That's a vector in HAB. And we want to take the inner product or scalar product with a vector psi1 tensor phi1. Well, then we just multiply it from the left. So we get here a psi1 tensor a phi1. And this is, by definition, again inherited from the constituent Hilbert space. No, not plus, sorry. Ooh, very important, it's a product. Times phi1, phi2. Again, very important that this is an inherited structure, and it's not necessarily obvious that if you make the composite Hilbert space inherit an inner product in this way, that it is indeed an inner product, that it obeys all the axioms. And you're very much invited to just check that. Does it obey the inner product axioms? Now, what I gave you in the past few lines was how you can take one of those vectors in the Hilbert space of the combined system and take the Hermitian conjugate of it. Now, this was not a generic vector. This was an unentangled vector. If you had an entangled vector, then you would have a linear combination of these guys. And then the Hermitian conjugate of the linear combination is obtained by linearity. And there's no need to spell that out, I suppose. You know how that works. Just keep in mind that linearity means, in particular, antilinearity under Hermitian conjugation. Because if you multiply that with lambda here, inside the bracket, then the Hermitian conjugation will get you a lambda star, a complex conjugate of lambda over here. Similarly, we wrote down here what the inner product is between two vectors of our Hilbert space of the combined system, namely this. But these vectors are unentangled vectors. Very simple form. What if we had a linear combination of these? In other words, what if we had entangled vectors here? Well, then you just have to write a sum here, and perhaps there as well, if both vectors are entangled vectors. And then you can just use the linearity rules that we had up there, the axioms, in order to pull these summations here in front, and then it reduces to, for each term, it reduces to this expression for how to evaluate all of this. All right, so now we have a means to calculate the inner product between the vectors of the Hilbert space of the combined system. Now from that, we can calculate the length of vectors. Inherit, let me write it like this. Therefore, HAB inherits a norm, namely, for all omega in HAB, we have that the length of the vector omega is equal to, by definition, well, what you get when you take omega and calculate the inner product with itself, and you know now how to do this here and there. And if the omega is an entangled state, an entangled vector, then yeah, you get a sum here, you get a sum there, get two sums. The whole thing needs to be evaluated by summing over both sums. Anyway, we can work this out, and then you also have to take 1/2 as usual. Okay, so now we can calculate the norm or length of vectors using this inherited form of the inner product. Remember, the general rule is this: when you have here a tensor product of two things, and here a tensor product of two things, the first factor in the product cares about the first factor here, and the second here cares about the second factor there. That's a general rule that's pervasive in all these calculations. All right, so it inherits a norm. So now we have a normed complex vector space, which also has a Hermitian conjugation, it has a dual, and so on. But from the norm, we obtain a distance. Therefore, HAB inherits a distance notion from HA and HB. How does that work? Well, the distance between two vectors, omega 1 and omega 2, and both of them are elements of HAB. This is also element of HAB. The distance between these two vectors is the distance, or called metric also, is the distance induced by the norm. Namely, we simply take the length of the vector, that's the difference between these two vectors. So we have here omega 1 minus omega 2. You see, if omega 1 is equal to omega 2, then the difference vector is the 0 vector, whose length is 0. So if the two vectors are the same, then we obtain that the distance is 0. Now, I don't want to spell out all the steps. We did this when we first introduced Hilbert spaces. Let me just remind you what then can be done. Once we have the notion of distance between vectors in our vector space, we then have the ability to define what is called a topology, which is a set of epsilon distance neighborhoods. And from that, we can define all sorts of things like continuity of maps. But also, we can define the notion of convergence of sequences. Therefore, obtain the notion of convergence of sequences. Psi n. So then we know what it means that a sequence of vectors psi n is converging towards a vector psi. And remember that so far we are only considering finite linear combinations of the unentangled vectors. But at this point, we are now ready to enlarge our vector space, HAB, to include also infinitely many sums of, of infinitely many terms, infinitely many unentangled terms, as long as the norm is finite, or as long as the Cauchy sequences are convergent. Now, it would take us a bit too far to review the whole business of Cauchy sequences, but please review it from earlier in the course. So the point here is that obtain the notion of topological completion of HAB by requiring the convergence of all Cauchy sequences. Remember, Cauchy sequences are sequences that want to converge because the distance between subsequent elements in the sequence tends to go to zero, or not just tends, but will go to zero. That's a Cauchy sequence. And a space is complete if, for all Cauchy sequences, there is a vector in our set towards which the Cauchy sequence is converging. This is how we complete the set of rational numbers to the real numbers, but it's also how we complete a pre-Hilbert space into a Hilbert space. And in principle, all this needs to be done. The upshot of it is that the elements of the Hilbert space of the bigger system AB consist are all those vectors whose length is finite, calculated as we did it up there. That's ultimately what is the upshot of all these considerations there. So now, one can check that we constructed or obtained the full Hilbert space HAB of the combined system of A and B. We knew that we had to be able to get a Hilbert space just because everything is quantum mechanical and we can choose our Heisenberg cut whichever way we want. And the proposition that I'm not proving here because it would be just tedious is that these are the correct inheritance rules that allow us to get to that Hilbert space from the constituent Hilbert spaces of the subsystems A and B. Now, what about the operators that act on the subsystem A and the operators that act on subsystem B? They represent observables, or I mean, some of them represent observables. And when we enlarge the Heisenberg cut so that we consider the combined system AB, then we can still observe the same quantities, but they must now be represented by operators that act on the big Hilbert space, on HAB. What are these operators? Now, in order to find out what the operators are, let us start with an important observation. Regarding operators. And that observation is that operators form a vector space. We're usually thinking of the operators as being objects that act on vectors. Operators map vectors of a Hilbert space into vectors of the Hilbert space. But it turns out that operators themselves also form a vector space. You see, the observation is operators can be added, and can be multiplied with numbers. Multiplied with numbers. Oof. With numbers. And remember what the axioms of a vector space are. A vector space is a set of elements which have the property that if you add any two of them, you get another element from the set. And if you multiply any one of them with a real or here complex number, you'll get another element of the set. So there have to be addition and multiplication rules that allow that structure, and that's what we have for operators. So therefore, operators form a vector space. Now, this, however, means that we can use for operators what we've just done for vectors. Remember, we started with the Hilbert space of system A and the Hilbert space of system B. And then we said that, we can define a new Hilbert space using the tensor product of these vectors and then linear combinations of them. And then we did other things, like we introduced the dual and Hermitian conjugation and inner products and norms and distance and limits and sequences with Cauchy sequences and completion and all that. But let's remember the first step. The first step was that we had two vector spaces, namely the vector space of states of system A and the vector space of states of system B. And then we figured out how to do the tensor product vector space. Let's just focus on this technique. Take an arbitrary vector space, an arbitrary vector space. You can put them together into a tensor product vector space. Now, in our case now, we are dealing with operators forming a vector space. There's the vector space of operators that act, that belong to the system A. And then there's a vector space of operators that belong to system B. And we can consider the tensor product of them. All of this is to say that the operators of systems A and B can be used to form a vector space of operators of system AB, namely by using the tensor product. By using the tensor product. So we don't have to invent a new tensor product. We just have to apply the axioms of tensor product now not to the states but to the operators. So what are then simple examples? So example, well, for example, if f hat is an element of HA, and sorry, it's not an element, that's not true. If f hat acts on HA and g hat acts on HB, then an operator of the tensor product space of operators is f hat tensor g hat. Then by linearity, we obtain a richer structure. We obtain also in this vector space all operators of the form sum over I f hat I tensor g hat I. So the f hat I are arbitrary operators acting on the Hilbert space of the first system. The g hat I are arbitrary operators acting on the Hilbert space of the second system, system B. And here we have a finite linear combination. Now, what are the rules applying to this? Well, again, there are inheritance rules. And this is really nothing new. We did this for the tensor product of vectors, and the tensor product of operators is exactly the same because operators are also vectors, but just in a different vector space, and the vector space of operators. So the inheritance rules are now that alpha f hat A tensor f hat B is equal to, and then alpha, and I hope you recognized how similar this is to what we had for the Hilbert space vectors, f hat B. And this is the same as if we put the alpha on the second factor as well. So we have f hat A tensor alpha f hat B. And then we also have the additivity. We have that alpha 1 f hat a plus alpha 2 f hat, sorry, no. This is also an operator from the first system, system A, but it's the second one. This is the first one. And then we take the tensor product with an operator of the second system. Then we obtain that this is alpha 1 f hat a tensor f hat b plus alpha 2 f hat a 2. This is one tensor f hat b. And of course, also the other way around, where the additivity happens on the second factor. So we have f hat a tensor alpha 1 f hat b1 plus alpha 2 f hat b2. And this is f hat a times alpha 1 tensor f hat b1 plus alpha 2 fa tensor f hat b2. Usual distributive laws here. At this point, we are ready. We are ready to come back to the original question. Come back to original question. I mean, one of the original questions today. Original question. Namely, remember, what we're dealing with is this situation. We have a system A, and we have a system B. And we are considering the bigger system AB. And then we said, that's all fine and good, but system A has observables. For example, f hat A. That's an observable in system A. And it's represented by the operator f hat A. Now, this is all good and fine as long as our Heisenberg cut is this. Because in this case, the f hat A is acting on the Hilbert space of system A, and we can calculate expectation values. For example, this system might be in the state psi. And then we can calculate f hat A psi, and there we go, we have a prediction, f a bar. Right, that's all good. But when we do our Heisenberg cut in this way, in this bigger way, when we include the other system here, then what used to be observable in system A still must be observable, still must be measurable from the perspective of the larger Heisenberg cut. So an observable, though, in the bigger system must be represented by an operator on the bigger Hilbert space. So then the question is, which operator represents this observable in the system AB? It must be some operator that acts on the full Hilbert space. F hat A, it cannot be, right? It cannot be F hat A because it acts on HA, not HAB. So which operator is it that represents the same observable but on the bigger Hilbert space? So this is the question, and here's the answer. The answer is, it is the operator f hat a tensor the identity operator. Right, so 1 is just the map, it's the operator that maps every vector space into itself. So this acts on, this operator acts on the Hilbert space HA. So acts on HA. This one acts on HB. And the whole thing acts on HA tensor HB, which, if you remember, is what we called HAB. Okay, so how? How does it act, and how do we know it's correct? So, how? Well, we have that f hat a tensor 1 acts on psi tensor phi. In what way? Well, this operator acts on this vector, so we have f hat a acting on psi tensor, this acting on that, so we have here just phi. Now, how do we know that that we actually get the correct answer? Check that f hat a really represents f hat a in the Hilbert space HAB. And we check that by checking whether the predictions come out right. So how do we do that? Well, the predictions are, so in system A, we calculate that the prediction for the observable f a is psi f hat a psi. We need to recover that result in system AB. In system AB now, we have state is psi tensor phi, and operator is claimed to be f hat a tensor the identity. If so, then fa bar in the big system, remember we are here we're still in system AB, then this observable fa, if really represented in the way that it is claimed, it has to be, well, dual vector psi tensor phi, then the observable, which is claimed to be f hat a tensor the identity, and then psi tensor phi, right? So it's vector, vector, and dual vector, and in the middle, the observable in question. Let's see what we get. This is then, remember this is a psi, f hat a psi. Always the first factor is interested only in the first factor. By definition, this is, if you go back to the axioms, this is how that works out. So psi, and then it's the, let me put it this way. It's psi, yeah, let's spell it out completely so that there's no mystery of it. So I'm just leaving this the same so far. And then we let this operator act on that vector. Remember we discussed above how that works. And what do we get? We get f hat a acting on psi. This is a vector. And then the tensor product with 1 acting on phi. So that's just phi. And then this is what? This then is psi f hat a psi from this tensor factor and that tensor factor, and then here the phi times phi. Just following the axioms from above. But phi, being a state vector, has length 1. So what we obtain is that this is indeed f a bar. So this is not circular, right? We were wanting to prove whether the observable calculated according to the prescription of system AB comes out the same as calculated according to system A only. And that's what we found. Here we did the calculation entirely in system AB, and we found it reduces to the calculation in system A only, because the second tensor factor just trivially became a 1. Now the same argument can be done with entangled states. It doesn't have to be psi tensor phi, it could also be an entangled state, and you would get the same conclusion. It's just more work to write it down. Now, what about special cases of observables that are particularly important? Special cases. Let's say we have the Hamiltonian of our subsystem A. Well, this Hamiltonian acts on the Hilbert space AB as Hamiltonian first system tensor the identity for exactly the reason that we just discussed. And the Hamiltonian of our subsystem B acts on the big Hilbert space as identity tensor H hat B. This means that we can now write down the Hamiltonian of the composed system, of the total system. So, therefore, the Hamiltonian total energy, and remember the significance of the total energy. From the very beginning of this course, remember there was Hamilton's deep insight that if you can write down the expression for the total energy of a system, then you can completely describe the system. Total energy contains all the information, because from the total energy function, from the so-called Hamiltonian, we can derive the equations of motion and therefore everything. So now the Hamiltonian, that is to say the total energy of system AB, is, well, what is it? H hat total, which is an operator that acts on the Hilbert space of the total system, is the Hamiltonian of the first subsystem, tensor the identity, right? It's HA, it's the energy that comes from the first subsystem, plus the energy that comes from the second subsystem. Well, this far it's correct if the two subsystems have nothing to do with each other. If they're very far apart from each other, then that's all. Then this is the total energy. This is the total Hamiltonian, simply because the energy of one system plus the energy of the second system is the energy of the total system. So it's a no-brainer to just add up the energies. But what if the two systems are capable of interacting with each other? Well, if the two subsystems are able to interact with each other, for example, one is an atom and the other one is an electron, well then does the total energy of the combined system only depend on the energy of the atom and the energy of the electron? No. There is also going to be a potential energy between them. You see, as the electron approaches the atom, it will start seeing the electronic cloud around the nucleus of the atom. If it penetrates the atom, it will even, if it penetrates the cloud, it will even start seeing the positive charge in the nucleus. And then as the electron scatters off and moves away again, it will climb out of that potential again. So an electron that interacts with an atom will certainly see a complicated electrostatic and, in fact, electromagnetic interaction between itself and the atom. Or if you take two electrons that scatter off each other, or two ions that scatter off each other. In fact, if any two systems interact with each other, it means that, classically speaking, there are forces between them, which also means that there are potential energies between them. But quantum mechanically means that these potential energies between them that depend on their distance and possibly on their velocity, quantum mechanically, these energies, the interaction energies, must be taken into account when writing down the total energy of the system. In other words, we have in general that when two systems interact with each other, we have here plus some h hat interaction. And that h hat interaction is never of this form, never of that form. Because if it were, it wouldn't describe an interaction, because it would depend only on one of the two systems. But then it's not an interaction Hamiltonian. Then we would say it's just part of the Hamiltonian of one of those two systems. A true interaction Hamiltonian is an operator that is a non-trivial linear combination, generally a non-trivial linear combination of operators. Here's something non-trivial, there's something non-trivial, and then sums of those. It could also be simply of the form, I mean, this thing could be e.g. Something like Q hat tensor R hat, where this one and that one, you know, they acts on HA, and this one acts on HB. But in practice, it could even be a sum over such operators. So interaction Hamiltonians can be complicated. Now, let's think back a little bit to the previous lecture, where we discussed Heisenberg cuts. And we said, when we have a quantum system of interest, and it is being measured by some other object, and that could be a measurement apparatus, but it could also be an electron, or it could be any size system in between just a single particle and being some macroscopic object. In any case, what we have is some quantum mechanical system of interest and a measurement apparatus. Schematically, we have a quantum mechanical system of interest, and we have some measurement apparatus. And then we said, okay, what's going on is that the measurement apparatus is measuring something about the system, and we're going to have some state collapse, a pure state, even if our system starts in a pure state, and then this measurement apparatus, let's say in the form of an electron, comes along, scatters off it. The pure state collapses with certain probabilities into the various other states, and since we don't know what the electron has measured, we have to assign a mixed state. So therefore, the evolution of our system is going from a pure state to a mixed state, with probabilities that we can calculate. That was one point of view. But then we said, wouldn't it be cool if we were to draw the Heisenberg cut this way? And all of this is a quantum system now. And then all of this collapsing of wave packets, collapsing of states would have to be explainable differently. Because in this bigger system here, system plus measurement apparatus, in that bigger system, everything is evolving without being measured, right? The only thing that's happening is that our measurement apparatus is interacting with the system. It is, as far as the physics is concerned, just the interaction of one system with another system. And that means that this interaction, whatever it might be, will show up over here. It will show up in this interaction Hamiltonian. So in practice, this interaction is described by the measurement process is described by taking a Hamiltonian that consists of the free Hamiltonian of just system A, the free Hamiltonian of just system B, in this case a measurement apparatus, plus the Hamiltonian that describes the potential energy that corresponds to the force that these two systems exert on each other. The interaction is always described by some sort of interaction Hamiltonian. And then this Hamiltonian, the total Hamiltonian, governs the unitary evolution, the evolution according to a unitary time evolution operator, according to the Schrödinger or Heisenberg or Dirac or whatever picture of that combined system. And then what used to be thought of as our system being measured by a measurement apparatus can now be viewed as those two systems interacting with each other through that interaction Hamiltonian. And that interaction is just some quantum mechanical process that doesn't disturb the unitarity of the time evolution. And it turns out, as we will see later, I just want to anticipate that a little bit, what in the older perspective looked like a wave function collapse, a state collapse, is happening when our stray electron is measuring our system. This state collapse from the bigger picture looks like some other mathematical phenomenon. Instead of the states of the system collapsing and pure state density matrix becoming a mixed state density matrix, no, instead, from the perspective of the bigger system, what happens is that before the measurement, the total state of the system, the total pure state of the system, is an unentangled pure state. Then, as the time evolution progresses, the state stays a pure state because we don't measure anything from the outside. It's a closed system, right? It always stays a pure state. But when the interaction kicks in, that pure state evolves continuously into a mixed, into an entangled state. So what we will later see is that what from one perspective looks like this subsystem going from a pure to a mixed state, from the perspective of the larger Heisenberg cut, looks like the pure unentangled initial state of the total system evolving into always a pure state, but a pure state that becomes an entangled state over time. So the big system being entangled means that the subsystems are mixed. Okay, this is one of the goals that we have in the upcoming material. Okay, this is as far as we got today. See you then.